Hello everybody. This is the last lecture in topic 09-1, the power stage dynamics, and the title of this lecture requires some explanation. And because first we'll start with buck boost converter. We already discussed the power stage dynamics of buck converter and boost converter. So now we turn our attention on this buck boost converter. So using this buck boost converter, we investigate the dynamics of all the three converters, and the buck boost converter will show the RHB0 in its duty ratio to output transfer function, and we'll discuss the DCM dynamics of this converter, what kind of change occurs in the dynamics of a converter if the converter goes into DCM operation. Actually, we went through this topic in the previous lecture, maybe 1 month ago. And the main thing is, as converter moves from CCM to DCM operation, the power stage double pole split into two dual poles because strong damping resistance embedded in the DCM dynamics of converter, and one single pole goes at low frequencies and the other single pole goes at higher frequencies. So if we are interested in the dynamics below the mid frequency range, the system effectively becomes the first order system with dominant pole at very low frequency, and this low frequency single pole generate very slow dynamics. So dynamics of converter in DCM is much slower than those of converter in CCM operation. That is the unique characteristic of DCM operation. After discussing this buck boost converter, and we'll go to this isolated converters. So power stage dynamics isolated converters are easily derived from the power stage dynamics of preceding converter at which the isolated converter is derived from. For example, the forward converter is derived from buck converter, and the flyback converter is derived from buck boost converter. So from the dynamics of its ancestor converters, and with some modification, we can come up with the small signal model of isolated converter, and from small signal model, the dynamics of converter transfer functions are easily derived with small modification. And maybe this is the kind of digression. So in the last part of this lecture, we'll discuss the construction of transfer functions from asymptotic pulse obtained from the simulation or experimental measurement from the process of analyzing or designing something, analyzing some power stage dynamics and designing the compensation of some converter. This kind of technique is come up, okay? We will confront many cases of deriving the transfer functions from the asymptotic plot. Okay, so we'll go through some details about this, not complete details, because the complete details is coming later. So we'll explain some basic idea about this, and this is the part of design-oriented analysis proposed by Dr. Middlebrook. Okay, so we'll start with circuit diagram of buck boost converter. This is the circuit structure of buck boost converter. So active switch is here, passive switch is located here, and this is common terminal as connected to the inductor always. Okay, so this is IL, and this is also IC. IC is defined as current coming out of the common terminal. So they are the same. Okay, so SPDT switch is located in this manner, some strange manner. It's a flat, okay, and it's laid down, all right. And the PWM switch model of this is shown here, okay. So originally this was VAP, DC voltage between A and P terminal here. So VAP is voltage across here, to there is this times this, right? Because polarity is reversed, so this times this is voltage across AP. So this is VS input voltage plus VO out voltage, and IC current leaving from common terminal is same as IL, and polarity of this one is output is reverse of that, opposite to this in voltage, means suppose this is the 0 and this is the 5 volt, then this can be any negative value because it can step up and step down this 5 volt. Okay, and this is the small signal model, right? Then you can perform the same analysis as the case of boost converter, and you have the result here. Okay, so this is the analysis result, small signal analysis result of buck boost converter. So very similar to the cases of the boost converter. This is the input to output transfer function. So you have D divided by D prime. This is the DC gain of steady state gain of buck boost converter is coming here. So this should be the DC gain. This is the input to output transfer function. Evaluate at DC is, of course, there should be the DC gain. Okay, DC gain and the ESR 0 and double pole here. Okay, standard coordinate term, and this ESR is determined this like this, and omega naught double pole frequency is this one. So LE is the same as the previous case. So this factor D prime squared is coming in the denominator, same as the case of the boost converter. This inductor is separated by this one. There are something in between transformer. So that because of that, so you have this, okay, and Q is given by this, and this assumption is used always. Sometimes I forgot to write this down, but you assume this thing is valid everywhere, and also it has this RHP0, but expression of RHP0 is slightly different from the previous case, okay, because of the some difference in this circuit structure, and this one is this one. So RHP0 is this one, but the worst case occurs when this is the minimum, that means maximum load current. When this one is a minimum, okay, then this one is maximum, then it becomes smaller, okay. Right, okay. So the worst case is low voltage, low line, heavy load, okay. The same condition as the boost converter, maximum working condition. So input is small and output is large, so you should work harder, okay. So it's the same case, so everything is the same. So this, you can move this faster, all right, same thing here. So this is two cases, RHP0 at higher frequency and RHP0 at lower frequency. So this right hand side one is worse because this phase basin is wider than this. So worst case occurs at the minimum input voltage and maximum load current. We call it low line, heavy load condition is the worst case. Okay. All right. And this is asymptotic plot. Low frequency gain, okay, and double pole and omega RHP 0 is coming here. It comes earlier than omega ESR is here, okay. But this occurs only in duty ratio to output transfer function. There is no omega RHP here and here, okay. We went through this, okay. Okay, so I don't have much to say here. All right, so let's move to another topic. That is power stage transfer functions in DCM, right? I said in the maybe beginning of this lecture, there are two operational modes. One is continuous conduction mode, and the other one is discontinuous conduction mode. And the simplest definition of that is the inductor current usually is continuous triangular waveforms for the buck converter case, something like this, okay? And average value of this is average value of this is IL, is IO for the buck converter case, okay? So you reduce this, you increase R. If R, right, R is increased, then this one will be reduced. Then there is just some constant will emerge, which shows this kind of waveforms. Okay. Here you decrease further. This inductor current will be something like this. Okay. So you go back if you want to know the details about this. Go back to my book, okay, and maybe chapter 3 or 2-3. Okay, so this is called DCM, right? Inductor current is start rising and reach maximum value and drops to 0 before onset of the next operational period, and it stays 0 for a while, goes up and go down. This is called discontinuous conduction mode. This one is continuous conduction mode. What is continuous and what is discontinuous? Inductor current is continuous and the inductor current is discontinuous. Okay? So criterion to determine DCM or CCM is inductor current. Right? So for this case, this is the buck boost converter example. So assume this is a PWM switch. Of course, this is the PWM switch, but converter is in discontinuous operational mode. PWM switch in DCM operation, and small signal model is different, very different. So this is the small signal model of converter, buck boost converter. Okay, so you can use any of 3 basic converters, but this one is easier to see because of the location of this switch. This is the small signal model. Okay, it's very different from the previous case, and a little bit complicated to derive this, but easy way of memorizing this is this one. This switch, active switch, is replaced by this 2 circuit component. One is RI. RI is a resistor. This one is the resistor. And this diode is replaced with the circuit. 3 parallel combination of this, and one of them is resistance. And value of this is relatively large, maybe 50 ohm and something like that. Okay, 70 ohm, something like that, very large. And this role of this is this RI and RO is very large, and it provides substantial damping. Okay, you know the Q is quality factor and is related with to the damping ratio. If Q is infinity, there is no damping. Okay, if D is Q is 0.5, that's critical case. If Q is smaller than 0.5, this double pole will separate into 2 real poles. That is okay. This is the example. This is a control to output transfer function of this buck boost converter. Okay, maybe I need some factor here. Maybe some DC gain KM should be here. Okay, and we have this RHP 0 and ESR 0. So numerator remain the same. But in the CCM, denominator was second order, 1 plus S divided by Q omega naught plus S squared divided by omega naught squared. Okay, that term is separated into two dual poles. So one is here, one is here. Okay, so in the CCM, the double pole was here, but in DCM, one pole moves to the lower frequency and another pole moves to the higher frequency. So there is a separation occurs. Okay, so this is the basic difference between CCM and DCM. Okay, and you can easily prove this distance of separation. So originally double pole was here, and one went to this side, and the other one this side. The distance should be the same. Okay. Now it looks different because my drawing was bad. Okay, but theoretically they have equal lengths. Okay, separation lengths. So with DCM, in DCM operation, you have this kind of characteristics. Okay. There are significant consequences on this. That is, this one is second order system. This one is, there is a one pole here at high frequency. We ignore this. We are not interested in this. But up to this is second order system, and this is what? First order system. Okay. So which one is easier to deal with? First order system is much easier. Okay. Than second order system. Second order system, we need some effort to design the stable feedback system. Okay. But in this single order system, maybe system itself is linearly stable. Okay, maybe some constant gain can be applied. It's not the case. Okay, but this one is very easier to handle. Okay, but if your converter will span the operational region of your converter will span both the CCM and the DCM. Now suppose your converter is designed for specific load current, maybe 2M, okay? And that is the DCM, CCM, and you designed your converter for the CCM. But inevitably, your converter will go to DCM if energy saving mode operation or some operational protectional mode operation, okay? This energy consumption is extremely important now. So there is just some energy saving mode, means this load current becomes a minimum. Then converter is obviously in the DCM operation. Okay. Then what should you use for your design? CCM or DCM? Answer is DCM. No, CCM. Okay. The reason for that is CCM is worst case. So if you make your converter stable for this worst case CCM, probably for the boost converter, low line, heavy load condition is absolutely worst case operational condition, then converter remains stable all the time. Okay? For the entire lifespan, the converter will be stable. Okay? But if you use this DCM, because the DCM looks easier, so you use this information, your control design, then if converter will go CCM, then your converter will be immediately, it will become unstable. All right? So everything will blows up. Okay? So that is the disaster. So this is important. Okay? So DCM characteristic is also important. So you will be learning this later. And this is a simulation example. Okay? This example is done with buck boost converter. So the reason I'm using buck boost converter is convenient to explain because the structure of this is very easier to remember, something like that. But result is equally applicable to the other two converters. Buck and boost converter, okay, it's the same result can be directly adapted to those converters. And I did some simulation, small signal simulation, using, I think this is the PSPI simulation, okay? And this is the case, this one is a case of CCM and this is the case of the DCM. Okay, so this double pole in CCM is split into two dual poles in DCM. One is omega P1, of course, this frequency. This is the theoretical prediction, and the other one goes to the higher frequency. This is the Hepto switching frequency. Okay, Hepto switching frequency. Beyond that, so it can be ignored because usually you are interested in up to this frequency range. Okay, in evaluating the stability and validating the performance of the converter, you are only concerning the frequency range far below that switching frequency. Right? So if converter moves to the deeper CCM, that means R is increased further, then omega P1 goes to lower frequency. Okay, so deeper DCM, right? And deeper DCM, it will go this direction, and there will be ESR 0, maybe somewhere here, omega ESR is coming later, and RHP, omega RHP is coming first, something like that, all right? And the slope is obviously -1, minus 20 dB per decade, and the phase remains this 90 degree flat, okay, plateau. That means system is a first order system. So this one is a second order system, and this one is a first order system. Okay, so let me finish this up. Okay, I prepared this in the previous lecture, previous semester. So it summarized the characteristic of converter, small signal characteristic converter in CCM and DCM. Okay, so this looks complicated. Okay, you don't have to remember everything now, but later on this will be helpful. Okay, if you study the end of this lecture, and this will be a good summary about the understanding the behavior of this PWM converter in DCM and the CCM. Okay, originally converter as a CCM, I think this is buck boost example, and the CCM double pole is here, and if you increase R like this converter, okay, originally it was this, R is increased in this direction, then converter still remains in CCM. So this is the CCM characteristics, second order CCM characteristics, and if you increase this R beyond some critical value, which is critical value is this one, then you increase further and further, so this poles split, okay, and further it moves for the lower frequency, moves to the further higher frequency with this. Okay, so this is the DCM and this is CCM. The characteristics are entirely different. One is first order system and the second order system. Okay, phase here is 90 degree. This is 90 degree, and the phase is decreased this minus 180 degree because double pole. ESR is coming somewhere else. Okay, so like that. So this is summary in CCM operation. This quality factor is larger than unity, and there is a double pole, and the midband gain. This is the midband gain of this transfer function is large, and this is small. Okay, and the phase change is fast. It changes abruptly at this frequency. Phase change is gradual here, slow, and this is the second order system. This is the first order system. Okay, so we are only looking at this frequency range, and system is first order, second order system, and the details about this will be covered later. Okay, this will cause some effect, profound effect on your control design. Okay, so this double pole characteristics. All right, one thing is this frequency, and this corner frequency determines speed of your converter. Okay, speed is usually determined by the pole, low frequency pole. The pole occurs at the earliest frequency. It's called the dominant pole. So dominant pole is here. So at the DCM, response is very slow. CCM is fast, but this is second order, so it can be oscillatory. Okay, there is no oscillation. This is this exponential type response, but response is very slow. Okay, all right. I think you can stop here. Okay, so we covered most of things about the power stage dynamics of PWM converter, and next lecture we'll cover the one remaining topic, small signal model, small signal dynamics of isolate converter, and then we move to the control of this converter, because we went through the details about the power stage dynamics, and based on that information you can proceed with control design. But before that, I need mention another topic, maybe 20 minutes, something like that, and after that we move to the next topic. Okay? Okay, we'll stop here. Okay, thank you. See you next Tuesday. I think we are about to discuss the small signal model or frequency response of small signal model of isolate PWM converters. But before that, I'd like to remind you one thing. We discussed the power stage transfer function of converter in DCM operation. So maybe some of you are not familiar with this topic. If that is the case, I recommend you go to this topic 8 and lecture 6. Okay, that is posted in the YouTube site, in the OCW site. The many things coming together, but in this YouTube site, I classified according to the topic of this. Okay, content of the lecture. So lecture 6 in topic 8 is discussing the details about the small signal dynamics of converter in DCM operation. Okay, so watching this video will help you if you don't have enough background on this. If you are okay, then you are okay. Okay, so let me go back to this page. So this is the circuit diagram of Ford converter. Ford converter is a type of PWM converter which is very popular in industries. Okay, and that converter is derived from the buck converter, so it's called buck derived converter. And this passive converter is called tertiary winding Ford converter. That means there is a transformer. So this is the isolation transformer. So this is called isolate converter, and transformer has 1, 2, 3 windings. This is primary winding, and this is secondary winding, and this is the tertiary winding. So this tertiary winding is necessary to reset the core of this transformer. So maybe you need some details about this, the topology of the PWM converter to understand everything. And then you go back to this lecture video, then everything is there. Okay, then assume you have some background of this. Okay, then this one is magnetizing inductance of this transformer, and this NT and the diode is applied just to reset this transformer. So this is the reset circuit, and the reset circuit does not interfere with the operation of the converter itself. The reset circuit just helps to reset this transformer. So without this transformer will be saturated and the converter won't work. So the only purpose of this is to make this converter working. So it's not involved with the small signal characteristics of this converter. So you take out this part, this magnetizing inductance, and along with this circuit. So all of this is called the reset circuit. So you ignore this. You don't have to consider this in thinking the small signal dynamics of this converter, so they are gone. Okay, so if you take a look at this, the structure of SPDT switch or PWM switch is not apparent. We have 3 switches, 1 active switches, 2 diode. Okay, but during the operation, the basic operation principle is if this is connected, then this diode is conducting automatically. And when this diode is turned off, then this is turned off and this diode is turned on. So in terms of its operation, this situation is very similar to the buck converter with one exception. That is, this diode can be replaced with this active switch. So in other words, in terms of its operation, you may consider this active switch is located here, this one. Okay, functionally it can move this here, then this converter becomes buck converter. Okay, so this is a buck derived converter. Then small signal model is very similar to the buck converter. Okay, this is the way of deriving or understanding the small signal model of isolate converter. So there is a transformer, but in terms of its function, the situation is almost the same as the case. This switch is moved to here. When this switch is turned on, then this diode will be turned off because of voltage across this secondary winding, and some current is built up here. Then when this switch is turned off, this diode is conducting. When this switch is turned on, this diode is reverse biased. So diode is off, and now this diode is turned on to create the freewheeling path of this inductor current. Okay, so in terms of its operation, the operation is very similar to this one. So the voltage here is referred to as VF. So VF occurs here. VF is this one, and this voltage, when this is turned on, this voltage becomes this voltage times turns ratio of this. So this value is NVS. Okay, when this diode is turned off or this switch is turned off, this diode is conducting, then voltage across this and this is 0. So VF reduces to 0. So this is 0, and this will be repeated like this. Okay, so this VF, and this voltage is applied to this part. This part is low pass filter. So output of low pass filter is something like this. So this, okay. In terms of its function, as I said, this is the same as this case, this one. And this voltage is applied to the input port of this low pass filter. Then output will be, this is the input voltage, this is the VF, plus minus, this is NVS, then output of this one will be average value of this. Okay, this is the same as the buck converter, except the voltage here, VF, is NVS. Okay, so this will be averaged to generate this average value as the output of this converter. Okay, so if you take a look at this active switch and 2 diode, three of them work together as functions as this SPDT switch, PWM switch. Okay, as I said, the structure of PWM switch is not apparent. And this active switch and this passive switch, they are isolated, separated with isolation with this transformer. But in terms of their function, that is the same as the role of this SPDT switch. The only difference is there is a transformer with turns ratio of 1 to n. Okay, Then small signal model is same as the buck converter. Some exceptions are there is turns ratio is changed from D to ND and IL is changed to NIL. Okay, because of the turns ratio of 1 to N here. Okay, so this can be modeled with this PWM switch, multiplied, cascaded with this low pass filter. But because of this, you have this factor N, and here maybe this is called scaled PWM switch model. Okay, so some people call it scaled PWM switch model. Then analysis of this circuit is practically the same as the previous case of buck converter. So following the same procedure, you obtain this. This is the PSPI simulation result of small signal model of tertiary winding for the converter. And this is the duty ratio to output transfer function, and transfer function is given by this. Everything remained the same, but in buck converter, this low frequency gain was D. Now we have ND because of presence of transformer with turns ratio 1 to N. Okay, and this frequency, double pole frequency, omega ESR, is the same as the previous case. So actually, this is buck converter, and you have double pole and 1 0, ESR 0, then double pole will reduce phase by 180 degree, and this pole will boost phase by 90 degree. Then final phase should be minus 90 degree here. So this should be the minus 90 degree. Okay, all right. This is one example, but you can apply this procedure. Many buck drive converter, there are converters called bridge type converter, full bridge converter, half bridge converter, or push-pull converter. So they share the same small signal model with extremely minor modification. Okay, all right. Let me consider this. This converter is called Flyback converter. This is very, very popular, even more popular than previous one, because this is very cheap, okay, very cost effective. This is the structure of converter. There is a transformer, and this is the magnetizing inductance of this transformer. So purpose of transformer is it provides the galvanic isolation to become an isolated converter, and this magnetizing inductance of this transformer is used as the functional inductor of the converter. Okay, for DC-to-DC converter, you should have an inductor to create the function of low pass filter. So you need the inductor, but inductor itself is coming from the transformer automatically. Okay, so transformer will be used as transformer plus inductor. So there is no inductor. For the isolation, they need at least one transformer, and with this, they can get rid of the inductor. That reduces the price of this converter. So this is very cost effective and very popular in the home electronics, consumer electronics. Okay, if you have a chance to work to have a job in the PWM converter area, probably you will deal with this converter. Okay, so this is extremely popular, and this is derived from the converter called buck boost converter. This is the basic circuit diagram of the buck converter. So this Flyback converter is actually derived from this buck boost converter, inserting transformers here. So this can be reduced to this. Okay, the procedure is explained in this lecture. All the details are discussed there. So this is kind of a conclusion. So the idea is you have a transformer, then one of the property of the ideal transformer is impedance at this part is deflected to this part, and the voltage is deflected to this. So this Vs is primary side of the transformer. Then secondary side, it will be this multiplied by turns ratio, and this Lm will be transferred N squared Lm. So this is equivalent buck-boost converter, and we know the small signal model of buck-boost converter. Then this is just the duplication of the small signal model of buck converter with minor modifications. Again, this Vs is changed to the NVS because of this, and this Lm is deflected to the secondary side. So N squared term is coming here, and NVS is coming here because of turns ratio of the N. So this is the small signal model of flyback converter. From this, you can derive the three basic transfer functions of this converter, following the exact same procedure to the case of buck-boost converter. Okay, so all the isolated converters has its original converter, then just modifying the original small signal model of original converter, ancestor converter. You can easily derive the small signal model of isolated converters. So this is one typical example, and I simulate the small signal model of flyback converter, and this is the result of the plot. I use the PSpice here. So this is the expression for the duty ratio to output transfer function. This is the DC gain. Okay, for the buck-boost converter, you have this, but you have N because of there is a transformer in front. Okay, and this is the RHP0. Boost and buck-boost converter, they have RHP0. So flyback converter has RHP0 because the flyback is derived from the buck-boost converter, and this is ESR0, and this is the standard second order term, and the expression for the omega RHP. RHP0 is this one. RHP is D prime squared divided by D, R divided by N squared Lm. So everything remains same. You have just this N squared term because of presence of the transformer. So let's think about the phase of this. So first we have double pole, so minus 80 degree phase delay, and we have omega RHP pole, but in terms of phase it behaves as the pole. So we have 90 degree phase delay, okay, and we have 0, ESR 0. Then final phase is minus 180 degree. So this final phase is minus 180 degree. Okay. All right. Before leaving this topic 9-1, I'd like to mention just one thing. This is the something different from the previous discussions, but this is also very important. It is closely related to the next topic of the control design. Okay. Suppose you have this type of asymptotic plot of something. Okay. Maybe this will be generated during the analysis and the design process, or assume this, you measured some converter transfer function of something, then maybe your result is something like this. Okay, or you obtained this curve from the small signal simulation using small signal model, or time domain simulation based on the computational method. Okay, then what is the transfer function of this? It's not easy to see here. Okay, but if you plot the asymptote of this, so asymptote of this is this one. This is low frequency asymptote, and this is the mid-band asymptote. and this is another asymptote, and this is another asymptote. Okay, always you can construct this. Of course, this is the approximation, but you don't have to be very accurate plotting this. Just use your ruler and something like that. Then watch the slope. This is plus 2 slope, minus 1 slope, something like that, and 0 slope, 0 slope. Then this is, there's a pole. This should be omega P1, and there's another pole, omega P2, and this is a 0 because of minus slope is changed to 0 slope, high frequency asymptote, then there is a 0. So omega 0 and midband gain. You observed this maybe assume this is 20 log km. Okay? Then it becomes this one. Alright? What I'm trying to say is this is not artificial one. If you have practically, there are many chances of meeting this type of situation from the measurement, from the simulation, from the analysis, or from the designing something, feedback controller, you come up with this. Then from this curve, you can easily write down expression of this, right? Because it starts from this differentiation at low frequency. So S is here, and KD is, this is a differentiation gain. Actually, if you extend this, you will hit 0 dB line somewhere. Okay, then this coordinate, this value is 1 over KD. KD, right? Small KD. 1 over KD. KD, why is that? Okay, so this is the first factor of your transfer function. Okay, so this factor is generating this. If you apply KD, 1 over KD here, this becomes 1. That is the 0 dB line. So the line segment crossing the 0 dB line offers the value of this. Okay, or you can find out this easily with some different method. Then you have this, initially you have this differentiation, then you have this pole, first pole, and you have another pole here, and you have 0. They are known, and the only unknown parameter is KD. KD is determined in this way by extending this, and okay, and finding out the 0 dB line here. That is one method. And another method, more desirable method, is consider this. Okay, only consider this, then this line segment, and the magnitude of evaluate at this frequency is Km based on this structure, this plot. So magnitude of this first component, first factor, evaluate at this frequency at J omega P1 is same as this one. Then you take out this log scale, and this is a linear scale, and you have this expression, and the KD is determined by this. Km is known, and this is known, then KD is known. Okay? So this is the way of constructing the transfer function from the asymptotic plot, or construction of transfer function from this measurement. Okay? You construct the transfer function in this manner, and you plot the Bode plot of this reconstructed transfer function and compare with original one. They are very similar. Okay, extremely similar. It's hard to tell the difference between them for many cases. So this is a very practical approach of this type of analysis. This is called system identification. This is the most primitive shape form of system identification. Okay, there are many techniques to identify the transfer function of system from the various measurement. Okay, this is one example. We have same example. Okay, but here somehow you want to use this value. So this is known, and this corner frequency is known already. Maybe this will be known, but you use this one this time. then TS is the same as the previous one, and you use the high frequency value of the high frequency value of this transfer function is this one. Then you just take the coefficient of this J term, then this one becomes this. So this is the high frequency asymptote, and this value should be the same as KH, like this. This is the identity in log scale. This is the identity in linear scale, and the KD is found. Then you have the complete expression of the transfer function from the asymptotic plot. Okay. So students, they are familiar with sketching the Bode plot or asymptotic plot from the given transfer function. You are learning that, okay? But more important thing is from the asymptotic plot or from the measurement, you should know to construct the transfer function, okay? There are some approximation, but that is very good approximation, all right? So you will be using this technique a lot. And in addition, this type of asymptotic plot itself will be come up with during the process of designing the feedback controller. Okay, so this technique is very, very essential. Okay, so this is the end of topic 9.1. Okay.